Okay, good. So, hello everyone. Today we have our seminars, Beyond That seminar series. And today our seminars will be with Dr. Yuanzhao Zhang. And it will be about dynamics on hypergraphs and hypergraphs from dynamics. So before I start the seminar, I want to briefly introduce who is Dr. Yuanzhao Zhang. So he's a physicist with Ph.D. from Northwestern University, advised by Adilson Motter. And after his PhD, he was a Schmidt Science Fellow at Cornell University, working with Steven Strogatz. And now he's a Omidyar Fellow at Santa Fe Institute. And his focus on developing math and computational tools for study of complex systems, especially using techniques from dynamical systems, network theory, data science, and machine learning. And recently, he has been working on high-dimensional basis and multi-stable systems, dynamics, and inference on high-order structures. So, yeah, thank you for accepting to come here and give this talk. And yeah, you can start. The floor is yours. Thanks, Angel.
No, thanks, Ricardo, for the invitation, and thank you for pronouncing my name flawlessly. But yeah, let's.
Yeah, I tried. I tried to do my best. Thanks.
I think I needed permission to share the screen.
Yeah. Okay. I think now you can share.
Yes. Okay. Let's see.
Yeah, perfect.
Okay. All right. So yeah, today I'm just gonna share some recent work we have been doing for the past couple years about dynamics on hypergraphs and how can we infer hypergraphs from dynamics. Um, so yeah, and just as the title advertised, I'm gonna divide this talk into two parts. The first part, we're gonna go from structure to dynamics and trying to understand things like what kind of, what role does hypergraph structure play in terms of shaping the dynamics we see on these systems. And then for the second half, I'm gonna go in the other direction and then talk a little bit about if we don't have a good model of the underlying system, can but have a lot of observational data of a time series, uh, which is the case a lot of times, can we infer something useful about the underlying interaction patterns of the system that is giving rise to the data we observe. Um, so yeah, so let's start with the first part. Since this is the Beyond the Edge seminar series, I don't think everyone here needs too much motivation about why high-order interactions are interesting. Uh, and I think if you ask different people, they are gonna give you different answers. I think, for example, an ecologist might tell you that, well, high-order interactions are interesting because, um, say, if you have two species interacting with each other, then you introduce a third species. That species, aside from interacting with the two species separately, it might also, say, modify the soil uh, for the first species, which alters the existing interactions. And that is something that is hard to model with, say, pairwise interactions. So that's one example in which you need high-order interactions to describe the system dynamics. Similar things happens in the brain, in which, say, a neuron firing may not stimulate neuron A and neuron B directly, but might modify the synaptic coupling strands between those two neurons. And that's, again, not something easily modeled by pairwise interactions. And from a dynamical systems perspective, high-order interactions actually arise very naturally from a technique called phase reduction. So here's one example of a nice experimental system people studied a couple years ago of several coupled nanomechanical oscillators. And each of them are described by a two-dimensional variable AJ, so it lives on the complex plane. Um, Physically, they are coupled to their nearest neighbors, as you can see using those solid lines. But very often people will say, well, two-dimensional dynamics, especially when they are coupled with other oscillators, it's still difficult to analyze. So can we reduce the dimension for the oscillators? And very often you can do what people call phase reduction. As you can see here, after the reduction, now each node is described by a one-dimensional phase variable. However, you do pay a price for this phase reduction in the sense that now the individual dynamics becomes simpler, but their coupling becomes more complicated. And especially, I want to point you to those terms which are the classical non-pairwise triadic coupling terms that did not exist before, which you can see as those dashed lines here. So, in a sense, even if you were only interested in physically pairwisely coupled systems, very often you would want to understand the effect of high order interactions in order to understand their collective dynamics. So here's a fun question. Now that we want to understand the effect of high order interactions on dynamics, where do we put them when we study our model systems, right? Say if you want to study the effect of high order interactions on, synchronization, contagion, population, right? What kind of structure should we study? Well, the obvious answer will be, we should study whatever structure you observe in the real world. If we want to study contagion, then we better use a real world, like human interaction network. Um, But the problem is, real-world data on hypergraph structures, they are still very rare, with some exceptions in social systems where you can measure those interactions directly. But obviously, it's much harder to, say, measure the non-pairwise interactions inside the brain, for example. So, so very often, as theorists, what people usually do is to start with some network data and then decide where to add hyperedges to construct a high order system. Now, there are two popular frameworks people use a lot to do that. One is hypergraph, which is kind of the most general structure to describe those systems with high order interactions. And then there are synchrotron complexes, which you can see here, which is a more constrained class of structures in which you need to satisfy this downward inclusion principle, meaning if you have a triadic coupling between those three nodes, then the three pairwise interactions on its boundary should also be included. And the simplicial complexes would allow us to use, say, techniques from algebraic topology to make the analysis easier. So people use both frameworks a lot. And the question that kind of got us started on our first project is, we were wondering, can we use the hypergraph and simplicial complex, those two frameworks, can we use them interchangeably, right? Are there any hidden consequences in choosing one over the other in terms of the conclusions we will draw on the dynamics? And for this, we will use synchronization as the dynamical process that we are going to look at. So I'm just going to show you fun videos that I like a lot just to demonstrate the idea of synchronization. So hopefully you can hear the synchronized swing in the end. Yeah, it's a simple experiment you can do on your kitchen countertop. Basically, the swing of the metronome kind of uh, drives the plank back and forth, and the move of the moving of the plank in turn provides a common driving force that sometimes can synchronize all the metronomes. Um, so a classical model people use to study the synchronization phenomenon is a chromatal oscillator, which is shown here. You have a phase variable describing each oscillator. Each of them has a natural frequency omega I, and they're coupled through this nonlinear sine function. And because we're interested in the effect of high order interactions, now we're going to add more terms. For example, we can, instead of a pairwise coupling term just involving psi j, theta j, and theta I, we would also have a three-body coupling function that involves theta j, theta k, and theta I. And we didn't choose those coupling functions arbitrarily. They actually emerge naturally from doing phase reduction on limit cycle oscillators. And for this study, we're gonna make two more simple assumptions. We're gonna assume the natural frequencies to be identical, and we're gonna just for simplicity, for the sake of simplicity, we're gonna focus on this uh, three-body coupling terms. So we're gonna ignore other coupling terms, but the conclusion would remain the same even if we included more terms. So basically, we want to study what is the effect of adding this non-pairwise coupling term on the stability of the synchronization solution that is theta 1 equal to theta 2 equal to theta n for all time t. So here is the kind of a summary of what we found. So we look at both random hypergraphs and random simple complexes. On the x-axis, we have a knob we can tune to decide. So we fix the total coupling budget, and we can tune, how much coupling resources is allocated to pairwise coupling and how much coupling resources is allocated to three-body interaction. So by tuning this knob, we can study, whether the non-pairwise interaction would help or destroy synchronization. And the y-axis basically tells how stable our synchronization state is. So you can see that as we give more and more weight to non-pairwise interactions in hypergraphs, the synchronization becomes better and better. But what was surprising to us it was that when you do the same thing for simple complexes, you actually observe the exact opposite behavior. The synchronization becomes worse and worse. So that's just like one striking example in which whether you use simple complexes or hypergraphs to model a system really matters in terms of the conclusion you will draw on the effect of dynamics, right? So, well, I'm not going to go into too much technical detail, but the way we calculate those synchronization stability is basically by, say, calculating the. Mhm. Okay. Sorry, is there a question? Okay.
I think no questions, Yuanzhao, so you can continue.
Okay. Yeah, so the way we calculate this diagram is to calculate the synchronization stability is by calculating the largest Lyapunov exponent transfers to the synchronization manifold, which is you need to do some numerical calculation, right? So can we get some more analytical insight or like some intuition on why hypergraphs and simple complexes give you the opposite trend? So to do that, let's try to link some obvious structural indexes to those two representations. Specifically, I want to look at how does adding those high-order indexes change the structural heterogeneity in sequential complexes and hypergraphs. So for example, let's look at a random sequential complex, and let's define a simple index called heterogeneity ratio, which is basically the ratio between the maximum second order degree over the minimum second order degree and divided that by the corresponding ratio for the first order degree. Now, what do I mean by first order degree and second order degree, right? The first order degree is basically the usual degree we see in graph theory, basically how many edges you have connected to each node. So for example, this node has a first order degree of 3. And the second order degree basically tells you how many triangles you have attached to each node. So this node has a second order degree of 1, whereas this one has a second order degree of 2. And this ratio basically tells us whether adding higher order interactions would make my structure more heterogeneous or not. If R is larger than 1, it means our structure is becoming more heterogeneous. Now, the really nice thing about a random sequential complex is, well, by the way, how do we construct a random sequential complex, right? We basically start from a Erdős-Rényi graph, and then whenever we find a closed pairwise triangle, as for example is the case here, then we attach a solid triangle representing a two simplex. So the really nice thing about this model is that we can actually write the expectation of K2 in terms of the corresponding K1 for that node. For example, let's look at this node, which has 3 edges. Well, what that tells me is that at most it can have 3 triangles attached to it, because you can pick these 2 edges, you can pick those 2 edges, and you can pick those 2 edges. So it's like choose 2 out of 3, and that is this term here. And of course, in order to be able to make it a sequential complex, we also need the third edge in the triangle to also exist. And this happens with probability P. So then you can write down the final expression for how many triangles you would expect in this structure. And by plugging this formula back into here, we would see that the heterogeneity ratio basically reduces to the ratio between K1 max and K1 min, which is always equal or larger than 1. So that tells us that at least for random simple complexes, adding those hyper edges would almost always make my structure more heterogeneous. And we know that a more heterogeneous structure is detrimental to synchronization. So that explains why adding those hyper edges makes synchronization worse in simple complexes. And actually, you can see this structural effect more intuitively because, just thinking about the process of adding those triangles, right? Where can you add those triangles? Well, you can only add them when you have those closed pairwise triangles, and that's usually some nodes that already have a high degree. So degree-rich nodes gets richer, and well-connected parts of the network become even more highly connected when we add those hyper edges. So that's the intuition behind it. For the random hypergraphs, I'm not going to go into details, but if you do the calculation, you can actually see it has exactly the opposite effect in that adding those hyper edges actually make the the structure more homogeneous, which in turn helps with making synchronization more stable. And finally, the one small thing is that, if we think about simple complexes, the defining characters, of course, is this degree heterogeneity, but there's also something else we can look at, and that can be important, is the correlation between the first order degree sequence and the second order degree sequence, right? Basically, which we call the cross order degree correlation. You can think of it as, if I have a vector of all the first order degrees and I have a vector of all the second order degrees, we can calculate their correlation coefficient. And the way the simple complexes are constructed, it usually have a really high cross-order degree correlation. Then we can actually do some simple operation, what we call the swaps, that we can preserve the degree sequence, but we can actually change the cross-order degree correlation. And by doing that, you can see we can actually change here. Number two basically means the maximum Lyapunov exponent that determines the synchronization stability. And you can see that we can actually change the behavior of the system very dramatically. So yeah, so just to conclude about this part, what we found is that the choice of whether using simplicial complexes or hypergraphs to model a system really has a dramatic effect on the collective dynamics we see. And because the structural heterogeneity is also important for dynamical processes beyond synchronization, such as consensus, contagion, percolation, diffusion. So we would expect that the same conclusion would hold for those other processes as well. So we really need to be careful in terms of which framework we use to study these dynamics. For example, people have did more detailed studies on contagion to look into more granular structures such as intra-order degree correlation, like the overlap between different orders with interactions, and they found similar behavior as well. Okay. So far, I mostly focused on linear stability, meaning, we look at synchronization, we look at how small perturbations would grow or shrink as we perturb the system a little bit. But what about a more global perspective, right? How does high order interactions shape the entire phase space more globally? So, um, so that's what I'm gonna talk about next. But first, let me just review what we know about this question in terms of pairwise interactions. So in this case, what we know is that there is actually very extensive multi-stability in when we consider large and sparse networks of identical chromatal oscillators. In particular, if we consider ring networks, so each node is coupled to the same number of neighbors, both on the left and on the right, then all the attractors we can show are the so-called twisted states, which here are three examples. Basically, as you go around the ring, the phase would increase by a fixed amount, and depending on how many times you go from 0 to 2 pi as you go around the ring, we can define a winding number. So here's q equal to 0, q equal to 1, and q equal to 2. And of course, people will have been interested in understanding in those multi-stable systems, what are the sizes of different basins corresponding to different twisted states. And there has been a lot of interesting work on, say, trying to establish the scaling relation between the basin size and the winding number of the basin, and also kind of the geometry of those high-dimensional basins. So in our work, we are again extending the classical identical chromatal oscillators on a ring to a kind of a hyperring in which if we use the language of this adjacency tensor Bij from before, then it basically means we would add a triangle if both node J and node K are within distance R from node I. Alternatively, you can also write this particular system this way. So Bij simply is a product of Aij and Aik. And here is a kind of visualization of this kind of ring structure, but with triadic coupling terms in our system. So we want to understand by adding those triadic couplings, how does it change the stability and the basin structure of our twisted states? So we can start with doing linear stability analysis for those twisted states, and it's very nice in this case because each twisted state's its stability is determined by a circular matrix, meaning you have this row. To get the second row of the matrix, you simply shift everything to the right by one, and you keep doing it. And for circular matrices, we can easily write down its eigenvectors and eigenvalues. So we can actually have an analytical expression that determines the linear stability of arbitrary twisted states for arbitrary coupling range. So this is exactly what we are plotting here. Again, we have the maximum Lyapunov exponent that determines the stability of the different twisted states. Q is a winding number, so here going from 0 to 80, so we study a system with 83 oscillators. Basically, this encompasses all the possible twisted states we can have in this system, and the y-axis shows their stability. So starting from no non-pairwise interaction at all from sigma triangle equal to 0, we gradually increase the high order coupling strength and observe and try to study its effect on stability. And to have a more clear picture, we can kind of zoom in around the origin, which is where you have the stability boundary. You can see that as we increase the high order coupling strength, more and more twisted states becomes stabilized. And interestingly, for example, for sigma triangle equal to 1 here, you can see that the twisted states actually become stabilized on disjoint intervals of winding numbers. So okay, so that's linear stability. The high order interactions make the twisted states linearly more stable. But now let's zoom out a little bit and try to look at how does it affect our basin stability. To do that, for example, let's take a kind of random slice through this high-dimensional phase space. Here I'm centering the origin of the slice at the twisted states with 12 twists. So you can see in the purely pairwise case without any high order coupling, the Q equal to 12 state is unstable. That's why you don't see any sign color in this basin plot. But then as we gradually increase the triadic coupling strength, you can see this sign basin emerging. Basically because from what we just saw from linear stability analysis, we know that those high order interactions will stabilize that particular state. But then, as we increase triadic coupling strength even further, you will see now the basis becomes much more fragmented, and there are those kind of black holes emerging, and those are what we call the non-twisted states. Those are new states that are created by triadic interactions that did not exist before, and they becomes more and more dominant, and they kind of squeeze out all the twisted states. So in this sense, although high order interactions make those twisted states linearly more stable, they actually becomes exceedingly difficult to find because of their basis gets shrunk dramatically. So you can see this more clearly in this plot, in which we are plotting kind of the relative basin size for each twisted states here. You can see that they kind of after a certain point they start to decrease rapidly and uniformly, whereas those non-twisted states becomes more and more dominant, and you can see it's like almost 100% probability even at moderate triadic coupling strength. So, so in this sense, high order interactions actually make the basins for those twisted states much deeper, but also makes them much smaller. So you can imagine this can be actually quite useful for a lot of biological systems, right? When you have deep basins, well, it's gonna be robust against small perturbations, which is what we want. We want our system to be relatively stable to small perturbations. But for example, for the brain to perform computations, we also needed to kind of switch between different attractors somehow efficiently. And that is what small basins are really good for. It makes it easier to switch between different states. So we think that high order interactions can actually be beneficial to those biological functions. Okay, so that's the end of the first part.
Yuanzhao, before we go to the second part, may I ask a question in the
Yeah.
previous picture?
Mm-hmm.
One back, please. To
Back.
this one.
Yeah.
So here, so you are changing this Q, and then it becomes like after a while, after two, non-monotonic change instead of monotonic, although everything.
Yeah.
Is there any idea why it's happening?
Analytically, no. Yeah, I mean, it's an interesting
Intuitive.
observation, right? So you're definitely right. In a sense, the triadic coupling makes those higher winding numbers more prominent to some degree before they all get reduced again.
Maybe
Yeah,
there's an optimality, right? So seems like
seems to be what optimality?
maybe there is some like optimal number for this thing to decay, or maybe previously before decaying again. So in this increasing part, so maybe some size effect or something. So
Mm.
it's little, I don't know. So I couldn't understand. I will read more to catch the idea.
Yeah, I mean, I don't think we have an explanation for, why
Okay.
Q equal to 4 goes up, whereas Q equal to 0 goes down. But like overall, of course, like because before this point, right, all the twisted like the entire phase space is occupied by twisted states only. So if you sum all of them up together, it's gonna all be at 1. And
Sure.
then at this point, they're gonna decrease together.
Sure.
They're gonna decrease. But yeah, like more granularly, is there something interesting happening? Also interesting that here it seems all the
Oh,
basins have roughly the same size, right?
yeah.
But yeah, no, like there are definitely lots of interesting open questions here. Like one thing we've been thinking a lot about is, how we have seen a lot of examples of those non-pairwise interactions inducing multi-stability, right? How general is this phenomenon? Like how much it depends on the specific dynamics of the nodes or the coupling function, right? Like
Uh-huh.
I don't think it's important to have chromatal dynamics here. I think you can observe similar dynamics in other systems as well. But can we have a theory of why do non-pairwise interactions induce multi-stability in general? I think that's still an open question.
Yes, yeah.
Okay, great.
Okay, thank you. Yeah.
Thank you. Yeah, so let me just spend maybe the last 10 minutes to kind of go the other direction and see whether we can reconstruct our hypergraph structure from time series data, right? Because I mean, I showed you that hypergraph structures are really important in determining the dynamics we see, but I still didn't tell you, what kind of structures we should use. And ideally, what we want is that we can actually infer the correct structure from time source data when we have them. Okay, and here we're kind of motivated by some interesting questions in neuroscience. For example, if we think about brain as some kind of coupled dynamical system, is it enough to model the brain as a network? Or do we need something more expressive, such as a hypergraph or sequential complex, right? In other words, do different brain regions talk to each other in pairs, or do they interact in larger groups in a more nonlinear fashion? And to do that, of course, we need a method that can infer causal high-order interactions from time series data. You can think of this as a generalization of the causal network inference problem. And for our purpose, I think one really important thing is that it must be our inference method must be model free, because in the sense that we should not assume we know too much about the dynamics on the nodes or how do the coupling functions look like, because obviously we don't have a reliable model for brain dynamics and for a lot of other complex systems. Technically, I think the key challenge is how do we distinguish a pairwise triangle between three nodes and a genuine three-body coupling between the three nodes by just looking at the dynamics they produce. Is this even possible? Um, and actually, the key idea we have is simply, you know, those pairwise interactions and those non-pairwise interactions. If you do the Taylor expansion of the underlying system, you will see that those different interactions would actually give you very different terms in the Taylor expansion. And this is largely independent of the dynamics of the nodes and the coupling function itself. So then we can actually just do some system identification, by applying sparse regression techniques to the time series data to extract the relevant terms, and then we can interpret those terms to find out, what are the coupling structures. So just to give you a little bit more detail, we can think of we can assuming starting from this kind of system. So Xi is the dynamics of the node I. It has some intrinsic dynamics described by Fi, and we don't assume that we know anything about Fi. There's some potentially pairwise interaction. There's some potentially triadic interaction. And our goal is to infer what is the adjacency matrix Aij and what is the adjacency tensor Aijk. Okay, so what happens when we do a Taylor expansion around an arbitrary base point, right? So we get a Taylor expansion. Now, what does it tell us if the coefficient between delta xj times delta xk is non-zero? Well, what it tells us is that if the coefficient is non-zero, it really tells us that the corresponding triadic coupling Aijk must be non-zero. And the reason being, regardless of what kind of pairwise coupling function you have in H2, because we are differentiating against both xj and xk, this term is always going to be zero. So the only way you can have a non-zero coefficient in front of delta xj times delta xk is when you have a genuine three-body interaction between xi, xj, and xk. So that's basically the basic idea. And we developed a data-driven inference method based on this idea. And we can first apply it to some toy systems for which we know the underlying ground truth. For example, here is the chromotal dynamics we have seen in the first part. Here, different curves correspond to different amount of data we give to our method. Here, it actually starts from just 10 data points all the way to 150 data points. This is true positive rate versus false positive rate. You basically want the curve to go straight up, then go to the right. So, here is the ideal spot where you have a very high positive rate, a very high true positive rate, but a very low false positive rate. And you can see even with like 20 or 30 data points, the method is already inferring 80-90% correct with very, very, very low false positive rate. Yeah, we can generalize this to high dimensional dynamics with chaotic dynamics. It all works really well. So then we can try to apply the method to EEG data as well to answer our original question. So here we applied our method to resting state EEG data from over 100 subjects. We divided the brain into 7 different regions, and we want to infer up to the first order interaction to see, like how important is non-pairwise interaction in determining these dynamics. And here is the result. Basically, the way to read this plot is, you start from anywhere on the heat map, then you draw 3 parallel lines, and where those 3 lines intersect, the axis is where how much each order of interaction contributes to the dynamics. So you can see that for the most part, the non-pairwise interactions actually contributes around 60% of the dynamics comes from those non-pairwise interactions. So they are really important in capturing the brain dynamics we observe. Another fun thing we can do is we can look at what are the most frequently inferred hyperedges according to our method. And here I'm showing you the 6 most prominent hyperedges from our inference. I should point out that all those hyperedges, they are directed and their directions are noted here. So for example, this means the node 3 and node 7 are jointly influencing node 1. And you would immediately notice that all those hyperedges, they are all pointing towards area 1, which is actually roughly the prefrontal cortex, and that is where a lot of the information processing is happening in the brain. So although we don't have a ground truth to compare our inference results against, at least with there are some interesting perspectives, we can look at it, and it gives us something that is sensible. So yeah, with that, just gonna thank my collaborators and thank you all for your attention. Happy to answer any questions.
Okay, thank you for the talk, Yuanzhao. I will stop the recording, then we can start with the questions.